Thank you for the short introduction. So maybe I will just say a few words about myself because the host is not here. So I'm a PhD student at CERN with the Frankfurt University, and I've been working in the past 3 years on this topic, machine learning studies in beam optics measurements and corrections. So yeah, and more probably you will see now in my slides. So here is the outline of a presentation. So after the short introduction, I will basically show the 3 topics I've been working on during my PhD time. This is the detection of faulty beam position monitors. Maybe some of you seen it in some other conferences or seminars, so I will rather go faster through this part. But I will show the concept and also some details to the isolation forest method, which I've been using. And then I will go to the to other topics, which are my...
¿Puedes avisar cuando sea la hora?
Sorry? I think someone is not muted.
Yeah. Yeah, please, if you don't speak, please mute yourself. Thanks.
Okay. So yeah, the other 2 topics, which are my more or less active fields of study now, is the estimation of magnetic errors based on the optics measurements. And there I will show some results on the simulations, but also on the experimental data. And then the third part is the denoising and reconstruction of optics functions by using the autoencoders, but also linear models. So let's start with the introduction. As I said, I'm currently doing my PhD, and the topic of today's seminar also happened to be my PhD topic. So there are 2 central questions, which are, first of all, before applying machine learning to some topics such as beam optics, of course, one should first figure out what are the limitations of the already existing methods, and then which machine learning concepts and algorithms can be applied in the most efficient way to address these limitations. And then, as I said before, I will also present some achieved results. But first of all, we and also I needed to understand in the beginning of my PhD why and how is the beam optics controlled in the LHC. I guess maybe something about myself. I'm not a physicist. I actually studied computer science, but now I do my PhD in physics. So excuse me if I will go into many details on the technical side. So yes, why and how is the beam optics controlled in the LHC? So we have many magnets installed all over the lattice in order to control the beam and to bring the beams to the collision points where the beam size has to be small. And by doing all this beam control, we have to face the fact that some magnets can have field errors or the alignment errors. And of course, these errors, they affect the beam optics. So these deviations from the desired design optics are then corrected by changing the strength of the magnet fields. And of course, in order to correct the optics, we also need to have reliable and precise measurements of the optics functions. And why is it important? Well, first of all, collision rate matters a lot for the LHC. So we need to control the beam size in order to have the desired number of collisions, but also to save the machine components from the damage of the not well-behaved beams. So what are the limitations of the traditional methods? So considering the measurements, there are specific instrumentations, such as beam position monitors, which we need to obtain the optical functions. And since this instrumentation can fail, this computation of the optical functions can be affected in a bad way by the faulty signal from the faulty instrumentation. So the limitation is that we need to actually detect the signal before we compute the optics function. Another limitation is that so current methods to correct the optics are based on finding the magnet strengths or settings which compensate the measured deviations of the optics functions. But this method, they don't really tell us about actual magnet errors which are present in the machine. Another problem is that, or not a problem, but the fact is that some of the optical functions, they have to be obtained by doing some additional measurements, and some sophisticated methods are needed, and which are not always possible to be performed given the limited time. So maybe one can obtain these optical functions without doing these additional measurements. Another problem is the noise, which of course ideally has to be reduced in order to obtain reliable optics measurements. And also we have to deal with missing data points. So we would like to reconstruct or to have some information about the optics at the points where we cannot measure directly. So I will start with the first topic, the detection of faulty BPMs. So first of all, I do obtain the optics function. So the BPMs, they record the turn-by-turn data, measuring the oscillations of the excited beam. And then by having the BPM reading, we can perform some harmonic analysis on this BPM signal. Before this BPM data has to be cleaned, but also after the harmonic analysis, there are some methods which are applied in order to clean this data. And then from this harmonic analysis data, one can compute the optics functions, such as the beta beating, which you can see here. So there have been specific cleaning methods already applied in optics measurements at the LHC in order to clean this BPM data, such as the 3D, or basically some signal-based cuts which are defined, or basically which are hard-coded and which are applied always to the measurements data. But in the optical functions, we still can observe some outliers, which we know are artifacts which are related to the faulty BPMs being present in the data. So that means that the cleaning techniques, they're not ideal. So we need something more between measuring the BPM signal, doing the harmonic analysis, and computing the optics function. So the idea is to apply unsupervised learning here. So the main change is that before we compute the optics, we cannot know which BPM will cause the outlier. So we need to somehow detect this outlier before we actually see that this is an outlier. And that's why we don't really know which exactly patterns are related to the faulty signal, or which properties of the signal are related to these outliers later in the optical functions. So that's why we need unsupervised learning, because we don't know the actual output. So we don't have this input-output pairs, which we would use for supervised training. And assuming that most of the BPMs measure correctly, the faulty BPMs can appear as anomalies. So there have been several tries applying such clustering algorithms as dbScan and local outlier factor, but the one which showed the best results was isolation forest. So the idea is that we apply isolation forest on the harmonic analysis data. So this is not that this data has to be computed or extracted from the BPM signal just in order to apply this method, but this data is there anyway because we need it in order to obtain the optics functions. So from the BPM readings, we go to harmonic analysis, then to do the cleaning by using the isolation forest, and then we can compute the optics functions. And hopefully avoid the appearance of erroneous signals. So a few words about the isolation forest method itself. So this is a decision tree based method, and forest meaning that it consists of several decision trees, and each tree in this forest takes random splits on a randomly selected feature in the data set, aiming to isolate each point. So that means here, for example, on this simple example, you can see that if a point is normal, then one would need a lot of splits, here 3, in order to isolate each of the points. But if it's an anomalous point, then one would need just 1 split in order to isolate this point. So one has to specify the so-called contamination factor, which gives an estimate of a fraction of anomalies to be expected in the given data. And this contamination factor first we just obtained empirically from the past measurements by just doing this cleaning on some historical data. And then later it was refined on simulations where the known BPM faults were introduced. And here is an example. So just to illustrate what data has been used for the actual detection of anomalies. So as I said before, these are the harmonic properties of the BPM signal, which is the tune, the main frequency found in this spectra, the amplitude of the signal, and the noise to amplitude ratio. So here you can see, for example, that by looking at this just in 2D, let's say, but just taking the 2 features, one can probably easily see what are the outliers, like this one or this one, but sometimes it's not possible. So sometimes one has to combine more data in order to see which signal is actually an outlier. And this is how it looks in the resulting optical function. So the blue points is the measurement of the beta beating, which is obtained from the signal which has been cleaned only with the SVD, and the orange is the cleaning in combination of SVD and isolated forest. And this method has been used in operation, so it's fully integrated into the optics measurements at the LHC. And there has been a paper more or less recently published on this. Now I will go to the next topic, estimation of the magnet errors. So about the optics corrections at the LHC, how is it done? So as I said before, that the correction methods, they actually aim to minimize the difference between the measured and design optics by changing the strength of the corrector magnets, which can be either individually powered quadrupoles or quadrupoles powered in circuits. So that's why by finding the compensating settings, we don't necessarily know the actual magnetic errors. We just know what are the powerings of the circuits which we need in order to get the optics which is closer to the design. And these corrections are usually done in at least 2 steps. So local corrections, which are focused on correcting the optics in the interaction points where the collision happen, and the global corrections using a response matrix method between available correctors and optics observables in the arc sections, so between the interaction points. And these global corrections are usually done for each beam separately. And here come the limitations. So first of all, we would like to know the information about the actual errors of individual magnets instead of the circuit settings. And also, so in case of the global corrections where the response matrix is used, in this response matrix, we also have the weights which correspond to each optics observable, which is included in this response matrix. And these weights, they have to be adjusted manually. And also, maybe there is a possibility to actually compute this optics correction simultaneously for both things. So the idea here is to use supervised learning and in the following way. So the idea is to build a regression model which takes as input the measurements of the optics functions and gives us as output the magnet errors. But here comes the first challenge. So as I said before, the corrections are done by using the circuit strengths, but the optics errors, they actually come from the errors in the individual quadruples. So we need to build training sets, training samples, which are which actually consist of the input, which is optics functions, and they're correlated to the known magnet errors, which will be our output during the training. So that's why here we will predict single quadruple errors instead of the circuits, because we need to have this known correlation between input and output during the training. So, and they also need a large data set here, but we don't have that many measurements of the LHC optics. And also because in the existing measurements and corrections data, we have the circuit strengths and not the single quadruples errors. So that's why simulations. And before going to a more realistic study, there have been also some proof of concept studies. There we actually perturb the optics functions in the training data by using the circuits. So we could have in the output also the circuit strengths, but in the validation data, or actually in the test data, so it's a bit, yeah. So we had the optics functions which were perturbed by the individual quadruples. And in this simplified study, we also compare different algorithms, for example, convolutional neural networks, which you can see here, the result of comparing the corrections obtained with the neural network and with the response matrix, giving pretty similar results. But in the end, we chose the linear regression as baseline model for further studies, just because it's easier to interpret, faster to train. And the most important reason is that mostly linear effects are introduced in the simulations, because in the first step, we actually correct the linear optics errors. And then step by step, increasing the complexity of the modules, we can explore the limitations of these basic linear models. So here just a few words about the regression method we've been using. So linear regression is pretty simple. I'm not showing here anything about this, but in order to control the overfitting and in order to get more stable modules, one can apply the regression method, which basically has a penalty on the update of the weights. So the module is less sensitive to the variation in the training data. And another technique is bugging, which is basically meaning that we combine several modules which are trained on a subset of the data, and then by averaging the results, one can get a more stable prediction. So this is how the data is generated, the training data. Here are many details about what optics has been used, but the important point is that so there are actually around 1,200 target variables. So the output magnet errors, and around 3,000 input variables, which are basically the optical functions such as phase advance, the dispersion at all BPMs for both beams, and also the beta at the BPMs next to the interaction points. There has been also the realistic noise estimated from the measurements added to the simulations, so in order to make them more realistic. So I used the scikit-learn implementation of the Riche regression and the bugging estimator, which combines 10 models. And in total, 18,000 training samples have been used. So not training, but the simulation samples, which have been then divided into training and test sets. So then, of course, there's a question how to evaluate the models. So one can evaluate such models from machine learning point of view just by comparing the predicted magnet errors with the corresponding true values. So for regression, one can use mean absolute error or the R square, which is explained variance. But for us, it's even more interesting to validate these models in terms of optics. So to see if the prediction actually also makes sense from the physics point of view. So for this, one could actually compare the optics, which was produced by the true magnet errors, to the optics, which can be simulated by using the predicted magnet errors. And here it's especially important to validate the how well can be the errors in the triplet predicted by this model, because the triplets, they control the beam in the interaction points, and here the beta functions are especially large, so the beam is very sensitive to the errors in the magnets. So we evaluate the triplet errors separately from the arcs errors, but the model predicts them all in one shot. So here are the results on simulations for the triplet errors. So here you can see the comparison or the relation between the true errors and the residual error, which is basically the difference between true and predicted values. And this slope tells us what is the systematic error of the trained model. So by considering the individual triplet magnets, we can see that systematic error is around 16%, but then we can actually combine these predicted values according to the powering of these magnets, because as I said before, the actual corrections are performed by trimming the circuits. So when we combine these individual quadrupoles into actual correctors, we can see that the systematic error becomes smaller, so which gives us the hope that the corrections will work even better than in case of the simulating the individual errors prediction. So here is the second part of comparing the results. As I said before, one can see how different are the optics errors which are introduced by the true simulated magnet errors and which are introduced by the predicted magnet errors. And we can see that they actually agree very well. So the difference between the beta beating, which is introduced to the simulated true magnet errors, and the predicted and the beta beating, which is introduced by the predicted errors, is around 1%. So for both beams and both planes, similar. And then we also tried to evaluate this model on actual measurements data. So for this, we took the measurements of the uncorrected machine from the beam commissioning in 2016. So it's pretty old data, but okay, can you still hear me? Because I got a message that my connection is weak. I guess it's fine. Okay, I just continue.
Still fine. Everything
okay. Okay. So for this experiment, we took the measurements data from 4 years ago. And because there we had the measurement of the machine without any corrections being in. So here, of course, we don't know the ground truth. So we cannot make this comparison between the predicted and true magnet errors, but we can see how similar are the optics errors which are introduced by the predicted errors to the actual measurement. So here we can see that they actually agree very well, the beta beating from the predicted magnet errors and the actual LHC measurement. So the overall RMS difference is about 7% and below 3% at the IPs. So hopefully by translating this predicted optics errors into circuit settings, one can get similar results, because that will actually save quite lots of time if one can do all this correction procedure just in one step by using this machine learning model. So now I will go to the third and the last part, denoising and reconstruction of the optics functions. So by performing these studies on the prediction of the magnet errors, we also noticed that actually these models are very sensitive to how much noise do we add to the input data, so to the optics functions, which are used as the input of the models. And we have seen that especially the prediction of the magnetic errors in the arcs suffers a lot from the presence of noise. So here you can see that this is a growing value, so this is a growing noise. We can see that the R square, which should be ideally close to 1, the explained variance, falls down, and the mean absolute error of the prediction of both triplet and arcs goes up, but the error of the prediction in the arc magnets, it goes up more than the prediction of the than the scores of the triplet magnets prediction. So actually when we do the simulations in the absence of noise, then we can obtain very high scores of these machine learning models. But of course, it's not realistic enough because in the measurements we will always have some noise. But the question is that maybe we can reduce the amount of noise in the measurements data. So, and this is one issue is that there can be also missing values at some of some optical functions, because as I said before, we have to clean the BPMs, and if the signal is cleaned, then there is no value of beta beating or of phase advance or the dispersion of the location of this cleaned BPM. So in the simulation data, of course, we don't have this problem, but in the real data, we will have to face this problem. And also, so the input features which are used for this prediction of the magnet errors are the phase advance, which is always available because it's like the basis of the optics measurements and optics analysis in general. But the dispersion and the information about the beta function at the BPMs close to interaction points, these functions, they need to be computed by performing some special measurements, which we don't perform always because of lack of time or just because something was not there. So that's why there is the idea to use machine learning to deal with these problems. And the idea is to use the denoising auto-encoder neural network, which is basically a neural network which consists of two parts, the encoder and the decoder. The encoder takes the input and it's compressing the input data to lower space. And then the task of the decoder is to reconstruct this data and provide it as the output. And by doing this encoding and decoding, one can reduce the noise in the data. One can also reduce the dimensionality of the data. It's also used in the generative modeling, and it can be used in both ways, supervised and not supervised. So now I will show how is it used for the reconstruction and denoising of the phase advance. So as the input, we give the simulated optics observable plus the noise and removing the signal at a few BPMs just by replacing the signal with 0. And in the output, we have the original full set of the optics observables at all BPMs and without noise. So this is the result on simulations. So the input here is the simulated phase advance deviations given the noise and replacing 10% of the values with 0. So this should reflect the faulty BPM signal. And in the output, we have the original simulated phase advance deviations, ideally without noise and without faulty BPMs. So for this, I used quite a simple neural network, just with 4 hidden layers, and just 10,000 samples have been used here compared to the 80,000 in the study before for the magnet errors prediction. So here you see the reconstruction of the missing BPMs. And here you see how one can reconstruct the, or not how, but the comparison between the simulated noise and the reconstruction error of the autoencoder, showing that the reconstruction errors is twice smaller than the simulated noise added to the phase advance function. And here is also the result of applying this method on actual measurements data. So here again, we took the same data as I showed before for the magnet errors prediction. And so here you see the reconstruction of all the phase advance at all BPMs along the lattice. And this actually shows that if this if the reconstruction everywhere is good enough, then we can also trust the reconstruction of the missing values. So yes, exactly. And here is another example how one can reconstruct the optics functions using the supervised learning. So here, this is the example of reconstructing the beta function at the IPs, because usually this is done by using the so-called K modulation method. But sometimes, for example, also in the historical data, which we maybe want to analyze again, this information is not available. And that's why one needs to reconstruct these values. So here, the input of the regression model is the phase advance deviations from the design model introduced by the magnet errors, and the output are the values of the beta beating at these BPMs close to the IPs. And here you can also see the comparison between the simulated and the reconstructed values. And the difference is around 1%, which is similar to the accuracy of the K-mod method, which is used to actually measure these values. And here is another example of reconstructing the dispersion. So this is similar to the previous examples. The input is again the simulated phase advance deviations, and the output is the dispersion function. Here again, the rich regression has been used. And also here, by reconstructing the dispersion function, we can see that the reconstruction error is quite small. So, okay, now I'm already at the conclusions. So I presented the 3 concepts how one can apply machine learning to the beam optics studies to 3 different problems. One was the detection of faulty BPMs. And this method, based on the isolation forest method, has been fully integrated into the optics measurements, and it has been operational during the past LHC run. So here you can see a summary of the operational results, where you can see that most of the remaining faulty BPMs, which remain there after applying the traditional cleaning techniques, could be cleaned by the isolation forest. So for the estimation of the magnet errors and reconstruction of the optics, so the main challenge is that the traditional approach of correcting the optics relies on the compensating the deviations of the optics functions from the design, but it doesn't tell us about the actual quadrupole errors. So by using supervised learning, we could estimate the actual errors in the individual quadrupoles. And so I showed the results on the measurements data only for one particular optic settings, but it has been tested also in the different optic settings. So hopefully this method is general enough to be able to make predictions also when the optic settings change. And the current limitations of this method are that, as I said, that only the linear error sources are introduced. And that's why linear models are used in order to predict these magnet errors. And another limitation, which I try to address with another machine learning method, is that the prediction of the arc magnet errors highly depends on the noise present in the measured optics. So here we could successfully demonstrate that we can actually reduce the noise, at least in the phase advance measurements, by using the autoequivalent neural networks. But also it was possible to reconstruct other optics functions by using supervised models. So outlook and the future plans are that the individual quadruple errors predicted by the machine learning models has to be translated into the actual correction settings. And that these machine learning tools, they still have to be integrated into the infrastructure of the LHC software. And this is all. Thank you very much.